Good evening, everybody, and thanks for coming. So I don't know very many of you. In fact, I've never met very many of you. But I am nevertheless willing to bet that at some point in your life, you have looked up at the night sky and seen all the stars and wondered, do any of those stars have planets? Are they anything like the Earth? Are there any creatures on those planets looking back at me and wondering exactly the same thing? Everybody has those questions, and that helps to explain why the field I want to share with you tonight, exoplanetary science, has attracted so much attention, both from scientists and the general public. Now, in most public talks, and certainly in the media, this field is portrayed as a single-minded quest for life, for other planets like the Earth, where we might one day find a new biology. And that is definitely one of the most exciting aspects of the field. And I will be talking about some of the progress that's been made tonight. But actually, that's not most of what I want to share with you. What I want to share with you tonight are some of the most unexpected, uninhabitable worlds, the ones that we didn't expect and that have taught us a lot about the full range of possibilities for a planetary system. So we will be studying strange new worlds. Now, first, in order for you to understand what's so strange about these new worlds, I need to remind you about what is normal. What was everybody expecting before the discovery of planets around other stars, of exoplanets? So let's take a short detour back to maybe the third grade, when you first learned about the solar system. And let me point out three striking patterns about the solar system that I hope your third grade teacher emphasized to you. One is that the orbits of the planets are nearly circular. Now, what's interesting about that is that there's no law of physics that says orbits have to be circles. In fact, in general, they are ellipses and can range from perfect circles to very highly elongated ovals. So the fact that the actual planets in the solar system have circular orbits seems to require some sort of explanation. And likewise, the orbits are nearly aligned with one another and with the rotation of the sun. Everything is nice and tidy and lined up so that the orbits are like grooves in a record, for those of you like me who remember what a record looks like. And that, too, was not a foregone conclusion. It wasn't demanded by the laws of physics. If the orbits were a little bit tilty with respect to one another, or if some of the planets were going backwards, it would be perfectly stable, nothing would go wrong. So the fact that we actually observe it in this very organized configuration also seems to demand an explanation. Then the third pattern is a little more subtle. It has to do with the composition of the planets. We have four rocky little planets, Mercury, Venus, Earth, and Mars, and they're all in the interior of the solar system. And then we have the large gaseous planets, Jupiter, Saturn, Uranus, and Neptune, and they're all in the far reaches of the solar system. So it's as if they've been sorted by size or by composition. It's too much to be just a coincidence. And so that pattern, too, seems to be a clue about where the solar system came from. Now, you probably are aware that Pluto meets none of these criteria. But we know what to do about that. We simply redefine it so that it is no longer a planet, and these patterns have no exceptions. So, how did we explain these patterns before the discovery of exoplanets? I'm going to tell you a little bit about the theory of planet formation that was developed long before we found planets around other stars. So the basic idea is that you start out somewhere in the galaxy with a large cloud of hydrogen and helium, the two most common elements in the universe, along with a sprinkling of dust, of little particles of silicates and metals and that sort of thing that make up just a small fraction of the total. Now, we're a little hazy on the details, but every now and then one of these clouds becomes unstable and starts collapsing under its own gravity. And so it all comes together. And what happens is, even if this cloud starts off with just random motions, any slight sense of rotation that that cloud has, a net rotation, gets amplified as the cloud shrinks under its own gravity. For some of you, all I have to say is it's the conservation of angular momentum. You might also think of it as the way if you spin a ball of pizza dough, it will flatten out into a disk. What happens is that that cloud becomes a flattened, rotating disk, a pizza, sort of hydrogen and helium. And the star forms from the material that makes it all the way down to the center and becomes dense and hot enough to ignite and become a star. Then what happens is that later on, the material that's in the disk gets together to form planets. And eventually the disk itself goes away, and we have a mature planetary system. So this explains two of those three patterns. It explains why the orbits are circular, because they all formed out of a disk in which all the streamlines were circles. And it also explains why everything is aligned with each other. It's because of that original sense of rotation that was inherited by everything. The fact that it came from a flattened disk and the star formed at the center of that disk certainly explains why everything is tidy and neatly aligned. Now, what about the third pattern, the one that's related to what the planets are made of? That's a somewhat of a longer story, and it has two parts. So here we are in one of these so-called protoplanetary disks, swirling hydrogen and helium, little flecks of dust. And the first part of the story is that called planetesimal growth. And what happens is these dust particles randomly collide with one another and occasionally stick together to make bigger bits of dust. And then those find each other and make small pebbles and rocks and boulders, and it's hard to believe, but you can actually work your way up to be the size of a rocky planet. So this theory, planetesimal growth, says that planet formation is very much bottom-up. You actually start with grains of dust, and you end up with planet-sized objects. So that's where rocky planets are supposed to come from. Now, what about the gas giants? That's the second part of the story. It's called core accretion. And the idea is you need one of these solid cores, these rocky planets, to get big enough so that its gravity is strong enough to attract all of that hydrogen and helium gas. Now, when does that happen? Turns out there's a critical mass. That ball of rock has to exceed something like 10 times the mass of the Earth for the escape velocity, the surface gravity of this ball, to be strong enough to start hoovering up all of the gas in its surroundings. Now, why does that only happen far away from the star? Right? The pattern is that the gas giants are all far away. Well, that's because in order to reach this threshold mass of 10 times the mass of the Earth, you need a lot of solid material. And that can only happen far away where it's colder and where you have things like water, methane, ammonia that exist as solids rather than as vapor, as they would closer to the star. So in other words, star systems, like mountains, are supposed to have a snow line, beyond which you have more snow to pack onto your growing planet, and that gives you a better chance to reach this threshold mass and swell up and become a gas giant. So it's a great story. It fits all three of those patterns beautifully, but of course it was invented to fit those three patterns, and you'd be forgiven for wondering whether it has any predictive power. And so that was one of the reasons, besides the quest for life, that everyone was very excited about the prospect of finding planets around other stars. Will they have these same three properties? Will the theory be validated by the discoveries and the properties of exoplanets? So we can go look for them. Well, there's a serious problem with trying to find exoplanets, and that is that planets are much smaller than stars. They don't emit much, if any, light of their own. They're just reflecting a teeny tiny bit of the starlight, and they are right next to the star. So the first thing you might think of doing is just using a good telescope, take a picture of a star, look for the little dots going around it that would be the planets. That almost never works. And the reason is that it has been compared to the problem of trying to spot a firefly buzzing around in the vicinity of a searchlight. Now, this is an image I've presented in many public talks. This is the Simons Foundation. I know that there's a lot of quantitative people around, so I figured I better check on this and see if the numbers actually work out. So I did some homework. What's the problem? The contrast between the planet and the star, of the light that's emitted. The star is spreading out its light over an imaginary sphere with a surface area of 4 pi a squared, where a is the orbital distance of the planet. The planet is only intercepting an area pi r squared, where r is its size, and then it only reflects a certain fraction of that light. And if you plug in the numbers for the Earth orbiting the Sun at its orbital distance, you get 3 times 10 to the minus 10. So it's a very challenging problem to find something that's a 10 billionth as bright as this object that's right next to it. So how does that compare to the firefly and the searchlight? Well, I don't know. I couldn't find any reliable data on the intensity of light from a firefly. However, I did find that the most intense searchlight in the world, according to Wikipedia, is the Luxor skybeam in Las Vegas. And if you're looking right down on that skybeam from above, that's 4 times 10 to the 10 candela. That's the metric unit for intensity. Whereas a candle is about 1 candela. Okay, so you have to find a candle that is sitting right at the apex of this pyramid here, with the searchlight blaring in your face. Now, what about the requirement on the resolution? How fine does your telescope have to be? Well, the separation in angle on the sky between the star and a planet going around it is the orbital distance divided by the distance to the Earth. You put in the Earth's orbital distance and a typical distance of a nearby star here, you get 1 part in a million, 1/1,000,000th of a radian. So what is that? That's the same ratio as a meter to 1,000 kilometers. So you've got to find your candle sitting right next to the searchlight for a meter away, and you have a telescope that's 1,000 kilometers away. That's what we're up against. And that's why this has almost never worked. So this is an image of the southern sky. I hope some of you have seen it. It's wonderful. It's a treat. And in particular, what you get to see is Alpha Centauri. This is the very nearest star system to the sun. So it's probably the best one if you want to go looking for planets going around it. It's so close by. Well, here's what it looks like if you take one of our best telescopes, the Hubble Space Telescope, and you point it at Alpha Centauri. Well, first you find out there's actually 2 stars there. It's not just one. There's a pair of stars going around each other. That's actually quite common. But there's no hope of actually seeing the little dots going around it. If the star Alpha Centauri is actually not this big physically. If it was a perfect telescope that could bring it to a perfect focus, it would be just a single pixel or less in my slide here. And a planetary orbit, something like the Earth's orbit going around it, would be something like this dashed circle. It's completely lost in the glare that we see in this Hubble telescope image. The reason is that no matter how much we try, we just cannot focus light as arbitrarily tightly as we would like. Even if we put a telescope above the Earth's atmosphere, which blurs our measurements, the laws of optics prevent us from focusing light to an arbitrarily small point. It's the diffraction limit. So that is why this direct imaging technique is mainly a job for the future, although it is just starting to work. And I'm going to show you the best example where it actually does work. So this is another star field. If any of you are amateur astronomers, you might recognize the great square of Pegasus here, this big quadrilateral here. There's a rather unassuming star on the border called HR 8799. And if you try to take a picture of that star, even with one of our best telescopes, it looks like this. This is not the actual image of the star. This is just the fact that we cannot focus the light down to a point and we see all of this glare. Nevertheless, some of my colleagues have invented cameras where they strategically place obstacles in the light path so as to cancel out most of the light from the star. And then, so they do that, they do a lot of digital signal processing, and they were able to reveal this. So here's where the star is. They've managed to zap out most of the starlight, and that has revealed these much fainter objects going around the star. Those are planets that are orbiting this particular star. If you're not convinced, wait a few years, keep monitoring them, and see if these dots move. And they do. You can watch them over the years going around this central star. So this is a beautiful case where that very direct method has worked. And we can see the planets, follow their orbits, and measure their brightnesses and all of that. This is the last direct image, though, that I'm going to show you tonight, and that's because almost all of our knowledge about exoplanets, apart from this sort of case, has come from sneakier methods, more indirect techniques. Okay, so what are they? Well, one of them relies on the fact that although we always say the planet is orbiting the star, that's actually a little white lie. They are both orbiting the center of mass of the planetary system, the average position of all the atoms in the planetary system. It's just that the star has so much of the mass that the center of mass is very close to the center of the star, but not exactly at the center of the star. So the star is orbiting too, as in this illustration here. The center of mass is at the plus sign. So the planet is going around, but the star is also going around. And that gives us our way in, because we've gotten very good at detecting motion of stars towards and away from us. And the reason is the Doppler shift. Doppler shift is the fact that if you have a source of waves, any kind of waves, and it is moving, then if you are on this side and it's approaching you, the waves are compressed and shifted to shorter wavelength, higher frequency. In the world of sound, that means higher pitch. In the world of light, that means slightly bluer. And if you are on this side and the object is moving away from you, the opposite. The waves get stretched to longer wavelengths. In the world of sound, that means lower pitch. In the world of light, that means it's slightly redder. So, how big is this effect? Well, so qualitatively what this means is if the star is moving away from us, it'll look slightly redder, it'll come around and look blue, and then back to red again. Okay. I'll get back to how big the effect is. Our second technique is even simpler to understand. It relies on eclipses. The fact that if we're really lucky, some of the planet's orbits will be oriented just so that they're carried directly across the line of sight to the star. So they're eclipsing their star. Oops, okay. Oh, I see. Well, here we go with the order of magnitude effect. I'll get back to the eclipse. Sorry, back to the Doppler shift. How big is the Doppler shift? The fractional change in the wavelength goes like the speed of the object divided by the speed of light. That's what c is. Very big number. Means that this is a very tiny effect. So if we insert the values for the speed of the Earth orbiting the Sun, the circumference of its orbit, 2 pi a, over the period of its orbit, 1 year, p, that would give us the speed of the Earth orbiting the Sun. We need the speed of the star orbiting the center of mass. So we take the speed of the Earth orbiting the Sun and we downweight it by the ratio of the Earth's mass, the planet mass, to the star's mass. You plug in the numbers here and you get 3 times 10 to the minus 10. It sounds just as bad as direct imaging, where we also got this tiny number. It turns out, though, that we can measure Doppler shifts even if they are so tiny. The technology has advanced to the point where we can sense these ever so slight shifts in color of the star. Okay. Then there's the eclipse method. The planet races across the disk of the star. We don't get to see that little shadow going across the star, but we do see that the star appears to get slightly fainter for the duration of the eclipse. Now, how big is that effect? Well, the fractional change in flux of the star depends on the area of the planet's shadow, pi r squared, where r is the radius of the planet, divided by the area of the disk of the star, pi times the stellar radius squared. So for a planet like the Earth projected in front of the Sun, that's 8 times 10 to the minus 5. Also a small number, but not as bad as 10 to the minus 10. And in fact, this eclipse method is much easier, as it has turned out, than the Doppler method for finding very small planets. There is a big catch, though, with the eclipse method, which is, what are the odds that the orbit is going to be lined up just so that the planet will go and eclipse its star? They're low. For a random observer looking at the Sun, there would only be about a 0.5% chance to see the Earth eclipsing the Sun. So you have to search hundreds of stars that all have Earth-like planets, even to find one of them that eclipses its star. So that's the downside of the eclipse method, is that you miss a lot of planets through the strict requirement that the orbit has to be aligned just so. And then even worse, suppose you were to see the Earth eclipse the Sun and detect that tiny signal. and you want to check if it's real. You have to wait a whole year to see if the eclipse is going to happen again. And you really want 3, just to make absolutely sure that you know what you're dealing with. So it takes a long time, and the duration of the signal is very short compared to the duration that you have to observe. So that's the big downside of the eclipse method. But these have both turned out to be very productive and have taught us most of what we know about exoplanets. Okay, so let's get to some of that knowledge. First of all, back to Alpha Centauri here. Alpha Centauri, I said, is the nearest star system to the Sun. Well, it turns out that there is a star in that system, a third star beyond the 2 that we looked at before, called Proxima Centauri, that is literally the closest star to the Sun. It's a little closer than Alpha Cen A and B. And there is pretty good evidence, not watertight evidence, but there's pretty good evidence for a planet around this very nearest star to the Sun that's not too much bigger than the Earth. And in fact, it seems to orbit in the so-called habitable zone of Proxima Centauri. What does that mean? That's the range of distances such that a planet's temperature, bathed by the radiation from its star, would allow for liquid water. Closer in, water would exist as a vapor. Farther out, it would all freeze. So the habitable zone is where there might be oceans on the surface of a solid planet. The reason we use the word habitable is that we tend to think that liquid water was very important for getting life going on the Earth. And so maybe that's how we should organize our search for life around other planets, by seeking places where there's also liquid water. So that's very exciting. Maybe you even heard about this discovery that was announced last August. A habitable planet, potentially habitable planet around the very nearest star to the Sun. If you did see the news coverage, it was probably accompanied by a picture like this, okay? Looking at this wonderful landscape with mountains and valleys and seeing the 3 stars of the Alpha Centauri system in the sky. Here is what we actually know about this planet. This is everything we know about this planet. Okay? The rest is artistic license. What we have here on the horizontal axis is time, and the vertical axis is the Doppler shift, the way that we sense the back and forth motion of the star. Each of these black points is a measurement of the Doppler shift, and the fact that you see them going up and down in this wavy pattern means that Proxima Centauri is coming towards and away from us, and that's how we infer the existence of this planet. Okay. So this is an example of Doppler data. And most of the data sets look sort of like this one, but not all of them. Let me show you some more Doppler data for one of my favorite stars. So again, we have time and Doppler shift, and each of these points is a measurement. But this doesn't look like that wavy pattern at all. What's going on here? So this star was, so negative means it's coming towards us. So it's coming towards us, accelerating a little bit, then it really started coming towards us, and then boom, it ran away from us, and then started coming towards us again. What is going on here? What is going on is that there is a planet around this star, but its orbit is not even close to being a circle. It is a highly elongated ellipse. This is a scale drawing of what the orbit looks like in comparison to the location of the star, which is orange here. And what Newton and Kepler taught us is that when you have one of these elliptical orbits, the planet goes much faster when it's closer to the star at one end of the orbit, because the gravity is stronger there. So what happens is the planet goes around once every 111 days, and it really whips around for a couple of weeks out of those 111 days. So this was one of the first major surprises of exoplanetary science, is that the orbits do not have to be circles. This happens to be a very extreme example, but the orbits in general for these giant planets are not especially circular. They're elliptical. So in fact, this was a gas giant planet. If you happen to be living on that giant planet or orbiting around it and looking at your home star, this is what it would look like for most of your year of 111 days. But then for a couple of weeks, the star would swell up in the sky by a factor of 30. So the seasons on this planet would be quite different from what we're used to. Okay, so those were some examples of Doppler data. Now let me show you some eclipse data. So here, time is also going horizontally, but the vertical axis is now brightness. How bright does the star appear in the sky? And at first glance, you just see a bunch of points that are kind of look like static. So this star is more or less constant in brightness. But then you see all these spikes going down. So every now and then at intervals, the star is getting a good fraction of a percent fainter, and then going back to baseline. You can zoom in on these spikes, and you can see that it's all happening over the course of about 4 hours. It gets fainter by 0.8%, and then it comes back to baseline. There is a giant planet going across the face of this star, periodically eclipsing it. Cool. What is really interesting, though, maybe you've noticed already, look at the time axis. Jupiter takes 12 years to go around the sun. These eclipses are recurring every few days. Very different. So what that means is that the planet must be extremely close to its star, circling around in a tight little rapid orbit. So this was the second major surprise of exoplanetary science, which is that you can have gas planets, presumably just like Jupiter and Saturn, but they're not beyond the snow line. They are about as close to the star as you can get. So contradicts that other pattern. So back to our scale model of the solar system here. If we wanted to place, if our solar system had a hot Jupiter, where would it appear on this map? Well, you wouldn't be able to see it on this slide. You have to zoom in, so we have to go into this central region here. Let's do that. Okay, so here's Mercury's orbit, here's the Earth, and this is what a hot Jupiter's orbit would look like. Completely mocks that whole song and dance I was giving you about how giant planets can only form beyond the snow line. Now, what about that third pattern that we haven't broken yet? The one that says that all the planetary orbits are lined up neatly like grooves in a record. Well, as it turns out, we found lots of hot Jupiters like this whose orbits are grossly misaligned with the rotation of their host star. I hope you're wondering at this point, how do we know that? Like, what sneaky, devilish technique can we use if we have a single point of light to figure out how the orbit is oriented? Okay? If you're thinking that, terrific, I'm proud of you, and I want to explain it. It's a little technical, but I cannot resist explaining it because it happens to be my own research group's obsession, and I just love explaining it. So bear with me. The way it works is you fuse together the Doppler and the eclipse techniques. So here's an eclipse. We can't see it like in the upper picture there, but we can sense that the brightness goes down during the eclipse. Now let's look at this eclipse wearing our special glasses that are extremely sensitive to tiny shifts in color, to Doppler shifts. Now what does it look like? It looks like this. The star is rotating. That means that half of the star, the material is approaching us. And on the other half, the material is receding. So it's approaching us, gets slightly blue shifted. On the other side, it gets slightly red shifted. Now, usually that just cancels out, and you observe no net red or blue shift. But if there's a planet that is eclipsing, and it's over the blue side of the star, then you do see a net red shift. Some of the blue light has been lost. And that turns into an anomalous blue shift when the planet is over on the other side of the star before the whole thing goes away. And this is our way in. This is exactly what we need to measure the angle between the orbit of the planet and the equator of the star. Because if it's all aligned, you'll see a red shift and then a blue shift like I just showed you. But if the planet is tilted at some crazy angle with respect to the stellar equator, it might be spending the whole eclipse on the red side of the star, and you would observe a blue shift throughout the whole event. Okay, so that's how it works. You perform these Doppler measurements specifically during these eclipses, and you get to measure that angle. And it turns out nature is kind and has served up all sorts of weird and interesting systems. So we have lots of examples, like in the upper panel, where we see red then blue. Those are well aligned. We have many examples of grossly misaligned systems, where the planet is apparently going over the north and south poles of its host star. And we even have some backwards or retrograde systems, where the planet's revolution is exactly opposite the star's rotation. Okay, so all three of those patterns are off. We have examples in which they're all broken. So I could spend the rest of this hour trying to explain how theorists have reacted. What went wrong with the theory? Did we tear it up and throw it out? Do we make amendments? But that's very much a developing story. And I would rather spend the rest of the time bringing you right up to the frontier of what has been observed, what has just happened in this field, and what is about to happen next. Okay. So what has just happened is the Kepler mission. This was a NASA mission. They launched a space telescope that was specifically dedicated to finding eclipsing exoplanets. We had our own space telescope. We didn't have to use Hubble or anybody else's. That for 4 years did nothing but monitor the brightnesses of hundreds of thousands of stars in a particular part of the sky, waiting for some of them to show these brightness dips and reveal the planetary systems going around them. And it did so just by having an enormous field of view and a giant digital camera. And by being above the Earth's atmosphere, was able to make these very precise measurements of brightness. Okay. So here, this shows you the improvement that we obtained by using a space telescope. On the top, this shows brightness versus time for a particular planet where there's an eclipse happening. You can tell, but it's very noisy. Those blue data points are scattered all over. This is the same exact system as observed with Kepler, which is actually a smaller telescope than the one we have on the ground. So this is why we go to space, to get these beautifully precise measurements of brightness. You can even see here where the planet was eclipsing, and it eclipsed a dark spot on the star, sort of like a sunspot. And we temporarily reduced the amount of light we were blocking, and you see these little glitches here. So you can see all sorts of detail in the Kepler data. So here's another example of real Kepler data. We have time on the horizontal axis and brightness on the vertical axis, but the brightness is now being measured in parts per million. Very, very precise. And this particular star has these periodic dips of around 200 parts per million. That means it's not, there's a planet there, not too much bigger than the Earth. And what's really stunning is that by this point, 2011, 2012, we had gotten used to the idea of giant planets going around once every 3 days, those hot Jupiters. But this one goes around once every 8 hours. This really is literally about as close to the star as you can get without being torn to bits. So the existence of these incredibly close-in rocky planets was revealed to us by Kepler. So this is what we know about the planet. We know its size from the amount of light that it blocks. We know its orbital distance and velocity from the repetition rate of these eclipses. So that's enough to get on the phone to a space artist and produce something like this, right? So these are called ultra-short period planets, or sometimes the evocative name lava worlds is given, because really any rock-forming minerals that we're aware of would be molten on the day side of this planet. So there probably really are oceans of magma swirling around on the side of this planet that faces the star. All right, here's another Kepler light curve. This may be one of the most important brightness records that Kepler monitored. What's going on here? So again, we have very tiny brightness variations, and it looks like just random static until you start seeing these dips here. But what's weird is there's not just some regular repetition of these dips. They seem kind of random. But then you stare at it even longer, and they're not random. What you have here is not just one sequence of dips, but 6 different sequences, each of which has its own period. This is a family of 6 planets that are all transiting or eclipsing. We use the word transit because we say the planet is transiting across the disk of the star. There are 6 planets eclipsing this particular star. And what's even more stunning is that all of the planets are on these compact, tight little orbits. If we compare this particular system, Kepler 11, to the equivalent orbits in the solar system, all of the planets' orbits would fit inside of Venus's orbit, which we saw is really in the interior of the solar system, and all but one of them would fit inside of Mercury's orbit. So this is amazing. Kepler revealed that there are these teeny tiny little compact solar systems elsewhere. But what's even more amazing is that these are not freaks. Okay? The hot Jupiters, the lava worlds, those are kind of freaky. Those only occur 1 every 500 stars or so. But if you pick a random sun-like star, there's something like a 10–20% chance it has one of these. And these were unanticipated by theories of planet formation. So I feel like this was one of Kepler's most important discoveries because it revealed a whole new mode of planet formation that's not freaky or outrageous, but it's quite common. Here's another one I really love. This is, again, Kepler data for a particular star, brightness against time. Here the scale is bigger, though. So this star gets fainter by almost 15% and then goes back to baseline. But then there are these other minor eclipses here that are only a few percent. And they're almost regular and periodic, but not quite. And you can stare at it for even longer, and the longer time series reveals this there are 4 different eclipse types here. There's one that's really deep, that goes down to 0.85, and then there are these other 2 that look a little bit different, but they're both just a couple of percent. And then there are those ones on the right that are really tiny, just 1 part in 1,000. What is going on here? What is producing all these very different types of eclipses around this particular star? What's going around it? Well, what's happening is here we have a pair of stars that are eclipsing one another. So we're over here, say, looking at this system. Star A eclipses star B eclipses star A. Those explain 2 of those sequences of dips. And then there's a planet that's going around both of them. And every time it wheels around, it eclipses one star and then the other. So that explains why there's 4 different types of eclipses here. And it all fits the model beautifully. There's no escaping the conclusion that there are planets whose orbits surround pairs of stars. They have 2 stars in their star system rather than just 1. And this was very exciting because the theory of planet formation, in that theory, it was very unclear whether such planets would exist. And that's because if you have 2 stars at the center instead of just 1, and they're moving around all the time, that would stir up all the dust in the rocks and maybe prevent them from getting together and forming boulders and then giant planets. So it was really up for grabs whether these planets would exist. But honestly, when writing this paper, we were at least as excited by the knowledge that George Lucas was correct. There are planets like Tatooine in the universe. They're not even that rare that the creatures on those planets would be able to enjoy a double sunset. So, right up to the frontier now, just announced a few days ago, was another very important result from the Kepler mission that has to do with the sizes of the planets going around the stars. So that distribution of sizes came into better focus because of observations that clarified the properties of the stars and therefore the planets. So we got a much clearer view of how big those planets were compared to the Earth. So here on the horizontal axis is planet size compared to the Earth, so the Earth would show up here. The vertical axis is how many planets per star do we find by scouring the Kepler data. And what's interesting is that we didn't know this before, but there are really 2 different categories of planets that Kepler has revealed to us. There are small planets and there are big planets. And there are very few planets in between with sizes of around 1.5 times the size of the Earth. The interpretation is probably that the planets on the small side are rocky. These are essentially naked balls of rock with no atmosphere because they're so close to the star that any atmosphere has been lost. So we're seeing purely rocky bodies, sort of like Mercury, but bigger. And on the other side of that gap, those are planets with just at least a little bit of hydrogen and helium gas. You add just a tiny amount of hydrogen and helium gas, it causes the effective size of the planet to be much larger and produce a much bigger eclipse. And so that's probably what we're seeing here, is a distinction between purely rocky planets and planets that are more like Neptune, that may have a lot of solids, but also have a lot of hydrogen and helium gas. Okay, so this is ripped from the headlines, just literally a few days ago. So as much as we love Kepler, and I do love Kepler, we still want more. We're never completely satisfied with the last space mission. So why is that? Well, there is one slightly annoying thing about Kepler, which is that so it looked at a particular region of the sky, and this is in the summer triangle, again, for those of you who are amateur astronomers. It looked in this particular patch of the sky, and in order to make a statistically significant survey, it had to look at the hundreds of thousands of faint stars that happened to be in that particular direction of the sky. So it looked really deep in that one direction and got lots and lots of stars. What that means in practice is that we find something in Kepler, we get really, really excited, something interesting, something we've never seen before. We want to use our ground-based telescopes to follow up, get the spectrum of the star, make a measurement of the angle of the planet's orbit with respect to the star, that kind of thing. And we're stuck because the stars are too faint. They're just too far away. even with our biggest, best telescopes on the ground. So we're in a very peculiar situation because of Kepler. Here we are in the galaxy. We're not at the center. We're out here. And Kepler happened to point in this direction and revealed to us all the wonderful planets that exist in this little cone here. But we know comparatively little about the planets that are right in our solar neighborhood. So that is the purpose of the next NASA mission that's intended to study exoplanets. It's called TESS, Transiting or Eclipsing Exoplanet Survey Satellite. It's supposed to be launched a little more than a year from now. And the way it will work is it will have not really telescopes, but glorified telephoto lenses that have very wide fields of view and very small openings, because we're looking at bright stars over the whole sky. All the brightest stars, they're scattered all over the sky. So you need an extremely wide field of view to capture them all and to monitor them all. So over the course of 2 years, TESS will use these 4 telephoto lenses to tile the sky and look for eclipses around the very nearest, brightest stars, hopefully finding the same kinds of weird and wonderful systems that Kepler did, but around stars where we can take those next steps and learn much more just because we have more light to play with. However, so I'm part of the TESS team. I'm very excited about this mission, but I'll tell you a secret. You don't really need a $200 million space mission to make pioneering discoveries in exoplanetary science. Okay. There's a trick. So here is a scale model of the sun and the planets in the solar system, and you immediately see the challenge of trying to detect an eclipse of a planet like the Earth projected against a star like the sun. Super tiny signal. You need to go to space to observe it. From the ground, the signal is about 10 times smaller than even our best telescopes can achieve from the ground. So the trick is to get rid of our obsession with sun-like stars and look at stars that are 10 times smaller than the sun. Red dwarfs that are actually not that much bigger than Jupiter. And in fact, these red dwarfs are more common than sun-like stars. We always say the sun is a typical star. That too is kind of a white lie. The typical star is more like this, or maybe a little bit bigger. The sun is kind of unusually, it's above average for a star in the Milky Way. And the great thing about these red dwarfs is if you put an Earth-sized planet in front of them, the signal is 10 times bigger, and you can detect it from the ground. You don't need NASA. What's the catch? The catch is that these stars are puny and very, very faint. So you need a bigger telescope from the ground, and you have to focus on just the very nearest ones to the Earth, and that means they're all over the sky in random directions. So you would have to somehow have a large telescope that could monitor the entire sky or lots of lines of sight looking individually at these tiny stars. But people have been doing that. So one of my colleagues in Belgium, Michael Gillon, built a dedicated ground-based telescope called TRAPPIST. It's a 1-meter mirror. The mirror is 1 meter in diameter. That is very modest by professional standards, but it is big enough to see these signals we're talking about. So what he did is he made a list of the nearest red dwarfs and just looked one at a time, staring at each one for a month, looking for any planets that happened to eclipse that one. If they didn't, he moved on to the next one and did them one at a time. He had no idea if he would succeed. Before these experiments, we didn't know whether such small stars had planets, and if they did, how commonly they occur. But it turns out nature was very kind. They do exist. And there is a particular star, and this is the constellation of Aquarius, that Michael was on Michael's list. By the way, there is no yellow arrow there. That would have made Michael's job much, much easier. But there is a star there. And this is what he found, right? This is probably, you may have seen this in the news coverage a few weeks ago when this discovery was announced. This is the view from TRAPPIST-1. Of course, this is just the artist's conception. Here is what we actually know about the planet. It's an eclipsing system of planets. So over the course of these observations, the star dipped in brightness in this very erratic-looking pattern. But again, what's happening here is we have multiple planets going around and eclipsing, each with their own period. And they're all superposed here. But you can pick them apart and tell them they each have different sizes, they each have different recurrence rates. So what Michael and his team found is a system of at least 7 planets, all eclipsing this teeny tiny star. And the planets are in the neighborhood of the size of the Earth. Presumably they're rocky, just like the Earth is. And also very exciting is that at least 3 of them are in this gray annulus here. That's the habitable zone of this star. So he has found 3 potentially Earth-like planets whose surface temperatures are conducive to liquid water around one of the closest stars to the Sun. This star is only 40 light years away, which is really right next door, galactically speaking. So some of you who are looking at the numbers might be a little puzzled. So the scale bar here is in units in which the Earth-Sun distance is 1, and all of these planets are within 0.06. This is an incredibly compact planetary system. All 7 planets have orbits that are within 6% of the Earth-Sun distance, these teeny tiny little planetary systems. How can that be the habitable zone? These are so close to the star. Well, the answer is that this star is pathetic. It's hardly putting out any radiation at all. So if the Sun were a stage spotlight, then TRAPPIST, this ultra-cold, faint star, would be a Christmas light. And if you want to stay warm, you have to get awfully close to that Christmas light to get the same radiation you would be receiving from the searchlight. So that's why, even though this is this incredibly tiny little planetary system, so here's the solar system, the TRAPPIST system would be something like this. You'd have to zoom way in order to see those 7 planets orbiting that tiny star, but 3 of them are nevertheless in the habitable zone of this very faint, very relatively cool star. So, how are we ever going to find out? We have these habitable planets. They're right next door. That's great. But how can we ever find out if they are actually inhabited? Right, what is the future of this quest? Well, there are 2 ways I'm aware of that people have thought of that might make this work. One, you build a big radio telescope, you point it at the star and you listen, and you hope that they're sending us TV or radio or some signal of some sort. This is the search for extraterrestrial intelligence. Certainly a valid experiment worth doing. We have no idea if it will ever work, right? What are the odds? We just have no idea. Then there's another method where we also don't know if it'll work, but at least the path is clear. We're going to get some information that will let us evaluate it in some more objective way. And that relies on looking at the atmospheres of these planets and looking for anything funny going on in the atmospheres. For example, the only reason we have so much molecular oxygen in our atmosphere is because the plants keep putting it there. Otherwise, after thousands of years, oxygen is very reactive. It would get locked up in the minerals. It would become oxides on the surface of the Earth. So if we could somehow look in the atmosphere of an exoplanet and see molecular oxygen, well, that would get the blood pumping. That would get you wondering if there are plants on that planet producing the oxygen. Fine. So how do we measure the atmospheres of these planets? How do we tell what's in them? We use another trick that's based on eclipses. The idea is that every atom, every molecule, has certain colors, certain wavelengths of light that it loves to absorb more than any other. So this is just a property of how atoms work, how the electron orbitals are set up in the atom. Every molecule has these characteristic colors that it absorbs more than any other. So for example, sodium happens to love a particular shade of yellow-orange. So what does that mean? It means that if there's a planet and it's eclipsing its star, there's going to be an atmosphere around that planet, and it's going to be partly transparent. And so some of the light from the star is going to filter through the atmosphere on its way to us. Now, if you view the same event with glasses that are tuned to just that shade of yellow-orange that only sodium loves, and if there's sodium in the atmosphere, suddenly the planet will look much bigger. And that's because the atmosphere has just become very opaque. All the sodium is absorbing that light. And so the planet will look bigger at that particular color than if you look at any other color. Okay. So I would have, if you had told me about this 10 years ago, or I guess 20 years ago now, I might not have believed that it would work, but it actually does. So you can do this experiment. As a function of the wavelength of light, this is a sideways graph now. So here we have these eclipse records where the star gets a little bit fainter and then goes back to baseline again. You get the data in each of these different colors, and you ask, how big does the planet look at that color? How about that color? How about that color? Now in this case, this is the apparent planet size as a function of wavelength. Nothing much is happening. We couldn't detect the atmosphere of this planet. Apparently it was too small, or it was too opaque for other reasons. But this has worked for some planets. Some of the giant planets with large atmospheres have been detected. So this is the apparent size of a particular eclipsing exoplanet as a function of wavelength or color. And the planet looks bigger in this particular shade of yellow. So that these investigators concluded that this planet has at least a little bit of sodium in its atmosphere. So the hope is that we can use this same technique not on gas giants, although that is interesting, but also on smaller objects, on rocky planets in the habitable zones of their stars. So when will that happen? We really don't know. So step one, finding the planets, that is underway. We will soon have some of the best targets. We will know where on the sky those eclipsing exoplanets are and what their sizes are, and we'll be able to make a rank-ordered list of our favorites, ones to go after. But then performing these measurements, which are much more painstaking, because you have to split the light up into lots of little colors, that I don't know if or when it will succeed. It might be possible to do with our next space telescope, the James Webb Space Telescope, which is due to be launched also about a year, year and a half from now. And it will be especially good at performing these types of observations at the wavelengths that we think matter. However, even for the Webb, to get a truly Earth-sized planet and to measure its atmosphere and look for oxygen may or may not be within reach. We might need the next space telescope. Okay, just to be honest. I hope it happens, and I hope that that sparks a big discussion about the atmospheric physics of these potentially habitable planets. And more broadly, I hope tonight I've enriched your stargazing experience. If you do go outside, you now know that some of these stars do indeed have planets. If you read up on this, you can even point to particular stars that you know have planets and learn about their sizes, learn about their masses, their orbits, and maybe one day we will even know which of those planets has life. So thanks for your attention.